AP Chemistry, Unit 2.5, Lewis diagrams. So Lewis diagrams are models that represent chemical substances and show the connectivity between atoms. They also display the bond order, single, double, or triple, between atoms, and represent the valence electrons that are not utilized for bonding. There are some conventions for Lewis diagrams. This is a Lewis model for water, dihydrogen monoxide. The maroon color is representing our chemical symbol for that atom. So the H and the O, those are my chemical symbols. The dashes in pink are used to represent the bonds and also are the same as 2 electrons being shown. Sometimes you'll see this represented as 2 dots, 1 dot on either side, or you will see this as kind of like drawn as a dumbbell so that you can see the dots on either side, but each dash is 2 electrons. And then any dots outside of those dashes that are showing the bonds are going to be any valence electrons not utilized in bonding. Lewis diagrams for individual atoms. For Lewis diagrams, we utilize dots to represent the number of valence electrons for any given atom. And so we would look at the electron configuration to determine the number of valence electrons. It's just going to be the highest energy level, and then you're going to just add up the superscripts to figure out how many dots you need. So for hydrogen, my electron configuration is 1s1, and so we just have 1 superscript, so 1 dot. For helium, it's 1s2, so 2 dots. Convention for helium specifically is to have those 2 dots be on the same side. This is to represent that it is not going to be a bonding availability. Instead, it is a non-bonded lone pair. For lithium, 2s1, so 1 dot, etc., etc. For simple molecules, hydrogen bonded with boron, carbon, nitrogen, oxygen, fluorine, and neon. We will end up looking something like this. So hydrogen with boron. Boron is a boron that only with 6, so we're just going to have 3 hydrogens bonded, no lone pairs on the boron. Carbon, we had 4 lonely electrons with 4 hydrogens, so 1 bond each. Nitrogen, we had 3 lonely electrons, 1 lone pair, and so we formed 3 bonds, 1 lone pair. Oxygen, we had 2 lone pairs, 2 lonely electrons, so we end up with 2 lone pairs and 2 single bonds. Hydrogen and fluorine, hydrogen has 1 lonely electron, fluorine has 1 lonely electron, so we have 1 single bond here, and then fluorine had 3 lone pairs, so our final form, we will also have 3 lone pairs. And then neon is a noble gas, and so no compound would be formed. Lewis diagrams for diatomic molecules. You are just going to go ahead and connect those lonely electrons, however many you need. Diatomic molecules, di means 2, so you should only have 2 atoms in your diatomics, and so however many bonds you need to get rid of all the lonely electrons is how many lines you would draw. We can prove a double bond forms based off of the bond energy. So fluorine, we can see that its bond energy was 155 kilojoules per mole, oxygen was 495 kilojoules per mole, and then nitrogen was 941 kilojoules per mole. So we can see a increase in bond energy between my single, double, and triple bond there. And then a reminder that the octet rule is going to apply, except for hydrogen and boron. Atoms are going to end up with 8 electrons around them unless they have an expanded octet. Continuing for our Lewis diagrams, we have a couple of ways that you could potentially draw out Lewis diagrams. One of them will show for phosphorus trichloride. So you can kind of mathematically work your way into the Lewis diagram. This is going to be best for anything where we're going to end up with an expanded octet or just not quite normal. So we would count the sum of the valence electrons for all atoms within the molecule, and adjust for any ions. So that would be removing or adding any extra electrons that are denoted by the overall charge for that compound. So for PCl3, phosphorus is in column 5, it has 5 valence electrons, and then Cl chlorine is going to be in column 7, so it has 7. And then there are 3 chlorines there, so that would be a grand total of 21 from chlorine, 5 from phosphorus, so a grand total of 26 electrons that I have to work with in order to make my compound. I'm going to go ahead and determine my central atom. Typically, my central atom element is written first. This isn't always true, but it's a pretty good place to start, hydrogen being the notable exception there. But you would go ahead and place others around it and then make sure that everybody is involved in the compound. And so we would touch phosphorus first. Since phosphorus was written first, everybody touches phosphorus at least once. After that, we would go ahead and subtract any electrons that were utilized in bonding from step 1. So each line, remember, has 2 electrons, so 2, 4, 6. So we had 26 total electrons to utilize, and 6 of them were used in bonding, which means we have 20 electrons left. We would go ahead and add any remaining electrons as dots to all of the atoms in the molecule, attempting to give each atom an octet. And then if we end up with anything other than a perfect octet for everybody, we have any leftover or we don't have enough or something like that, that's when we would circle back and potentially look at double bonds or triple bonds to go ahead and satisfy the molecule's Lewis structure. Another example that we're going to go ahead and look at is going to be for sulfur dioxide. So sulfur dioxide, we have 1 sulfur, 2 oxygens. Both of them have 6 valence electrons. So we have a grand total of 18 electrons to work with. Again, I'm going to go ahead and put sulfur in the middle since it is the first element listed, and then put a single bond for each oxygen there. That takes care of 4 electrons, so then that would mean that I have 14 electrons left to go ahead and distribute to everybody. If I did that, this is what I would end up with, where sulfur does not have an octet. And so this is a problem, and I know that this isn't going to be correct. So I would have to circle back, since all of the valence electrons have been added and I wasn't able to achieve an octet for my sulfur. I need to go back and add a double or triple bond to make that satisfactory. And if I turn one of the oxygen to sulfur bonds into a double bond, then everybody would end up with an octet, and so that would be a viable Lewis structure.